Hi everyone, I'm Maxim Lukyanov, Product Manager at Snowflake, working on machine learning and data science.
Hi everyone, I'm Sri Chantala, Product Manager at Snowflake, focused on Snowpark. If you're interested in accelerating your data pipelines in Snowflake using Python's familiar syntax and thriving ecosystem of open source libraries, in this demo, we'll show you how.
To show you Snowpark for Python, let's go back to our global retailer, StyleMeUp, whose rapidly growing e-commerce channel has been experiencing transaction fraud. To reduce costs related to fraudulent transactions, StyleMeUp wants to implement a fraud detection solution that leverages machine learning. Let's see how their data engineering and data science teams can use familiar programming concepts and APIs and a rich ecosystem of open source packages available within Snowflake to collaborate and build the solution. For this demo, I will play the role of the data engineer tasked with preparing and enriching the data for the data science team. And Maxime, who you will hear from soon, will play the role of a data scientist in charge of developing and deploying a fraud detection model. To start, I need the right data. I find two relevant customer transaction datasets, the orders and order details tables, which contain more than 500 million transactions. I'll need to explore these to better understand what data preparation is necessary. I'll do this using a Jupyter notebook. Using Snowpark API, I easily set up a connection between Snowflake and my local notebook instance. Taking advantage of the data frame abstraction and integrated pandas support in Snowpark, I quickly visualize the data in the order details table. I see it includes details about what items were sold, their value, and their associated transaction ID. And in the orders table, I see transaction-specific information such as the IP address, shipping and payment details, and the total transaction amount. There is also a column which indicates if the historic transactions have been manually tagged as fraudulent or not. This is exactly the information we need to build a fraud prediction model. We can now engineer additional features that might be useful for the data science team. Maxime has a hypothesis that knowing whether or not an IP address was masked, the distance between the order placement and shipping locations, and the average price per item in a given transaction could be other useful features for predicting fraud. I know there are third-party datasets available on the Snowflake marketplace that can help me enrich the IP addresses to create the first two features. After a quick search on the marketplace, I find IP geolocation and IP address privacy detection datasets from the data provider IPinfo. Another team at StyleMeUp has already purchased these datasets, giving me immediate access to them. Using these datasets, I can quickly enrich our IP addresses to get the required information. I do a fairly advanced join on the IPinfo privacy dataset to determine if the IP address was masked or not. With the Snowpark data frame API, I was able to express this complex join logic as concise Python code. Additionally, I've written a simple function to do a similar join on the IPinfo location dataset to get the geo-coordinates for the order placement location using the IP address and the geo-coordinates of the shipping location using the shipping zip code. Now that I have the geo-coordinates, I can calculate the distance between the two locations. To do this, I use the GeoPandas library and write a simple calculate distance function and register it as a user-defined function in Snowflake. With Snowpark for Python, I have access to hundreds of curated open source Python packages, including GeoPandas, pre-installed in Snowflake from the Anaconda Secure repository. To execute these packages in Snowflake, I don't need to do any manual installs or manage any dependencies, as the Conda package manager is natively integrated. When I call the calculate distance function, it returns our new IP to shipping distance feature. And most importantly, all my custom Python code got pushed down to Snowflake and ran seamlessly in a highly secure sandboxed environment built right into the Snowflake processing engine. To derive our third and final feature, I joined the orders and order details tables to calculate the average price per item in a given transaction. Combined, these tables amount to over 2 billion rows, which is not a small amount of data to process. As this runs, Let's look at the query history in Snowflake. In the query details, I see the SQL generated to process our various Snowpark queries. Here, I can also see the temporary Python UDF created on the backend to run our custom calculate distance function. Now that the query to calculate the average price per item is complete, we can see that Snowpark made efficient use of the Snowflake engine to do a computationally intensive aggregation for over 2 billion rows in just under 8 seconds. As a final step, I combine the original dataset with the newly created features and write the results to a new Snowflake table. Maxime and his team can now use this enriched data to test their hypothesis and build a machine learning model. Maxime?
Thank you, Shri. As a data scientist, my next step is to build and deploy a fraud prediction model using Snowpark for Python. I will start by taking a sample of the enriched dataset to visualize it in my notebook and get a better sense of the new features that Shri has developed. First, I will create a Venn diagram to see the relationship between fraud transactions and masked IP addresses. There is clearly a significant overlap between the two, which is a good signal to leverage in my predictive model. Next, for the distance feature, I will plot IP address locations on the map. The size of the overlay circles correspond to the distance to the shipping address. The larger the circle, the farther the distance. And the orange color indicates fraudulent transactions. There seems to be a significant number of large orange circles which indicates a correlation between distance and fraudulent transactions. So far, this new feature seems promising. Let's go ahead and quickly train a fraud prediction model using XGBoost and scikit-learn directly in the notebook. The resulting model shows a high level of accuracy of 89%. When I plot the feature importance chart, I see that the 3 features Shri engineered are most important, confirming my original hypothesis. Specifically, the masked IP feature obtained from the Snowflake data marketplace surfaced as a top contributor to the model's predictive power. Based on these results, let's run this model in Snowflake to make predictions at scale on the new transactions. To do this, I will deploy my detect fraud function to Snowflake, which is incredibly easy with Snowpark. I simply add a UDF decorator to the function and specify which Python packages the function needs. Snowpark detects that my function uses the scikit-learn model object we just trained and automatically packages and deploys it to Snowflake. Now I can use the detect fraud function in my Snowpark data frame query to generate predictions for 1 million records in the new transactions table. Within a few seconds, the query is complete. Without moving any data out of Snowflake, I was able to get the predictions the e-commerce team at StyleMeUp needs to reduce transaction fraud. When I go to the query details in Snowflake, I can see that the detect fraud Python function was a computationally expensive operation that took a significant part of the query execution time. Yet Snowflake Elastic Performance Engine was able to efficiently distribute the computation of this function to run model inference for 1 million rows in under 10 seconds. Looking at the SQL query, you can see that the detect fraud function is now available as a SQL function. This is a very powerful property of Python functions, as it extends Python support to all parts of Snowflake that work with SQL. For example, I can use this function in Snowflake task to run predictions on an incoming stream of new transactions as they happen. If you are interested to learn more about additional Snowpark for Python scenarios in Snowflake, check out the upcoming deep dive session later today called What's New? Snowflake for Data Science. Let's recap what you just saw. The data engineering and data science teams at StyleMeUp were able to enrich data, build and deploy a machine learning model to predict fraud. Using Snowpark for Python, they were able to use familiar tools and programming language while still benefiting from the scale and performance of Snowflake. With Anaconda integration, they had direct access to a rich ecosystem of Python open source libraries without any associated package installation and dependency management challenges. And with the built-in secure Python sandbox in Snowflake compute resources, there was no need to move data out of Snowflake. Snowpark for Python joins the family of languages already supported by Snowpark, including Java and Scala. If you want to be the first to know when Python becomes available in public preview, sign up at snowflake.com/snowpark-for-python. We are really excited about Python joining the family of languages already supported by Snowpark, including Java and Scala. In the comments, let us know what use cases you are most excited about to build using Snowpark for Python. Also, make sure to hit the subscribe button and turn on notifications so you'll be the first to know when we put out a video. For more information on Python, go to snowflake.com/snowpark-for-python. Thanks so much for watching.